I want to say a few words about signals. Signals are the quantities that we deal with in electronics. We normally process a signal in some way. We enhance it, we modify it, we do something with it. And in particular, we're interested in developing a common nomenclature so that when we are discussing electronic signals, we're all talking about the same thing. So a physical signal is basically any time varying quantity. So that might be temperature, humidity, flow rate. It can be literally anything. It might be one-dimensional, like temperature. It might be two-dimensional, like a video signal, for example, an image, two-dimensional image. But the physical signal, in order to be processed by an electronic circuit, has to be transduced into an electrical signal. And that's usually either a voltage or a current. So we're never dealing with the actual signal. We're dealing with an analog of that actual signal. And that electrical analog is the thing that we process in our circuits. And so that's where we get the expression analog signals. So we manipulate the analog signal rather than the physical signal itself. So the analog signal, the physical signal is transduced into the analog signal. We process it, and sometimes we then transduce the analog signal back into the physical signal, depending on what it is we're doing. For example, if we are designing an audio circuit, we typically take the sound pressure wave from a microphone, which is then converted into the electrical signal. That's the analog signal. We do something with it. For example, we might filter it, cut out some noise, something like that, or we might amplify it. And then we will transduce it back into the physical signal via a set of speakers, for example. But all of the processing is done on the electrical signal and not the physical signal, which is the sound pressure wave. Now, there's lots of different ways of classifying signals. For example, we might decide to discriminate between deterministic and random signals. And just to give you an example, a deterministic signal is generally one that we can write down an equation for. So if we had something like a mains power supply voltage, we can write down an equation involving the maximum value of this sinusoid, the frequency, and some phase. And using that equation, we can predict the future value of that signal extremely accurately. But we can't do that with all signals. For example, we can't write down the equation for the words that I'm saying now. Okay, there's always this random component to it, and it's just too complicated. And instead, we have other mathematical techniques for dealing with that. There's lots of different ways of classifying signals, but for us, the job of talking about different types of signals comes down to two very simple things. We really just want to know what is DC and what is AC. So the DC component of a signal is simply its average value. And as we'll see soon, the average value is very important because in order for the electronic components to work, and I'm talking about things like diodes and transistors, we have to establish certain DC levels in the circuit in order for those devices to operate. For example, transistors have to be biased. That's the word we use to express the idea that we have to arrange for the voltages around the transistor to be in certain ranges in order for the transistor to operate as an amplifier, for example. So the DC values in a circuit are generally the things that have to prevail in order for the circuit to work. And the component that we are actually interested in processing is usually the AC component. And for us, the AC component is simply that part of the signal that varies or deviates about the average value. So when we're writing down equations describing how a circuit works, we might refer to the voltage at a particular node by, V subscript A. Well, are we talking about the average value or the AC value, or perhaps a combination of both? So we just have to have some agreed nomenclature. So for example, here is a sine wave which is offset. So we can write down the equation for this thing. It's 3 plus 2 sine 2 pi 50t. So hopefully you can see that the average value of this signal is 3. And it deviates by plus or minus 2 volts about that average value. So it goes up to a maximum of 5, comes down to a minimum of 1. Now, I've got some labels drawn on this diagram, and when the primary symbol is a capital and the subscript is a capital, that means we're talking about the average value of a signal. So I'm suggesting that this signal exists at a particular node in a circuit. So big V subscript big A is the DC value at that node. The AC component is represented by the primary symbol and the subscript both being in lowercase. So small v subscript small a represents the deviation about that average value. And oftentimes we want to talk about the combination of those two things, so that if we had, for example, an oscilloscope connected with DC coupling, the small v as the primary symbol with a capital A as the subscript, that represents the instantaneous total value, if you like, of the signal. So that's the DC component plus the AC component. So for this example, it's very easy to identify what the bits are. So the DC value is simply 3 volts. The AC value is the bit that deviates about 3, which is 2 sine 2 pi 50t. And small v subscript large a, that's the instantaneous value, so the AC and the DC component, if you like, the total signal. So you can see why it's important that we have to agree on this, because otherwise, we won't be speaking the same language. And that basically is all there is to it. We all just have to agree to stick to these rules.